Hello, everybody, and welcome to the Music Production Podcast. I'm your host, Brian Funk. On today's show, I have Valery Vermeulen, who is a electronic musician, a math teacher, a data analyst. He's got a lot going on. He's using data from black holes to make his latest album. There's so much cool stuff that's going to be probably a bit over my head, and I've already explained that to Valery, so he knows, and hopefully it'll be an interesting conversation, but I think it's a really cool way to create music in untraditional ways, sort of futuristic ways. When I first heard about you, Valery, I saw your website, music production/cybernetic sound design, and right away I was like, awesome, it's futuristic, it sounds... I thought of the Terminator, and I thought of just this sort of like dystopian future that I think we were kind of getting to a little bit. How we're in such an interesting time in the world where so much is changing so fast, and we need to really be careful before we turn too many knobs and open too many doors for an interesting future. But I'm really happy to have you on the show. Welcome.
Yeah, thank you for having me. So I'm also very looking forward to the conversation. So
yeah, this is a really cool thing that is definitely new to me. A way of creating music using data from black holes. If I'm understanding this correctly,
yes.
I'll tell you just a short backstory. I did. Do you remember? I'm sure you do. A couple of years ago, they captured the sound of gravitational waves.
Yes, of course. Yeah.
So I took a sample of that and put it in and made a drum rack out of it and made some, playable instruments with it, which I thought was really fun. But I think that is just very much the tiniest tip of the iceberg of what you've gotten yourself into.
Yeah, I saw that. I think I saw that on YouTube. Yeah. It was really cool. Yeah, I didn't stumble upon but yes, it was shown to me, so it's very nice.
I was marketing it as the oldest drum sound ever made.
And did you you spread it around probably then the whole drum rack, or?
Yeah, it's a free download for Ableton Live users, so that you can use probably, I guess it's like a millions and millions of years old sound that finally reached Earth.
Yes, it's true. Yes, yeah. So I had a little bit of similar experience. So with Mikromedas, it's a project that started in 2014. So it's quite a while ago, and it started, in fact, as a commissioned work for a festival, the Dutch Electronic Arts Festival, and my brother, who's also doing space art, but more visually. He invited me to do a commissioned piece for the festival, and they wanted to do something on space and sound. That was a little bit the topic, because at that time I studied music production here in Ghent. So that's the city where I'm living. It's a city in Belgium. When you're studying music production, normally they train you to produce pop music. So I was trained to produce pop music and then more direction electronic music. But I got a little bit stuck in the whole EDM genre, kind of electronic dance music, and then this project came along, and normally it was a one-time thing, so I would only do it one time. That was the original idea. And then I started looking at NASA and seeing if I could maybe do some things with some data from space and deep space. And then this is how the first performance series, because we call it performance series for Mikromedas, got into life. And the idea was to make a sonic representation of a voyage from Earth to the center of the Milky Way, only using sound, so no visuals. And there also I could use some data from some neutron stars, some recordings, and they were approximately, I think, 28,000 years old, the same as you had. Well, not a million years old, but it was the same principle. And when they come from 28,000 light years away, it means that the light, because the signals are electromagnetic waves, and light is a special kind of electromagnetic wave, they take 28,000 years to reach us. So, and in your case, yes, it should have been millions of years. So, yeah.
This is a pretty cool thing in far as it's got this thematic thing that you've defined beforehand.
Yeah.
Right, so you came up with this idea of the space music, right, and the journey into the center of the galaxy. And I guess that really would inform a lot of the decisions you make as far as the music, the sound, the sources of the sound as well?
Yes, of course, because, of course, what I always try to do is use my own imagination. It's just a very nice inspiration, I think, to work in that field. Because everything is possible. A lot of things, okay, people have worked with space sounds, but you can make it your own. And of course, I like to work a little bit then as a scientist. For example, for the piece on the journey from the Earth to the center of the Milky Way, first I had to figure out how can you get there. So and then you cannot use Google Maps or something like that. So you have to start digging. Like, okay, first you go in the Milky Way, and then in our galaxy, and then you go out of our galaxy. You have the Kuiper belt, and then you have the outer region of our solar system. But the further you go, the less things are unknown. And then you try to figure out which data is available, what data can you use, and then based on that, you can make tracks on, for example, you can make a track on the rings of Saturn, or you make a track on this, of course, the Sun, or you make a track on Neptune, or you make a track on a cluster that is further away. So that's a little bit, it's a little bit like every track is a small kind of scientific project in which you try to generate sounds, inspiration, and then once you've cooked enough material, you can make a whole track out of it, or you make a couple of tracks and then you choose the best track. So yeah,
I like how having this thematic idea gets the wheels turning, and I think in so many projects I've worked on, and a lot of people that actually like get their work done, it usually starts with this idea. It's so fun to go into your studio and just be like, let's see what happens. But when you have this picture, now it's more of like you've got the canvas already. Now we have to fill it in. We have to flesh it out. It's a great way of working. I think I'm curious though. So you're taking, I guess, numerical data from. You said from Saturn's rings. So how?
Yes.
How does that become? Music.
Well, for those tracks, sometimes you also can use some sonifications that were done by, for example, NASA has done some sonifications, or ESA. So that's and other things. There's a lot of material from the Voyager satellites, numerical data, that you can also get. And then the thing is then you have to program your own synthesizers to do the sonification. So there's two ways to do that. That was for the first series of Mikromedas, and that has a first EP, but the EP was never released. I just put it on SoundCloud. You also see it on my website. But it's only after the first project, I wanted to go, because I'm also trained as a mathematician. So I was specialized into the mathematical theory of superstring theory. And superstring theory is a theory in which people are looking for ways to combine quantum physics and general relativity. So quantum physics is the physics of everything that's super small. So the smaller you go, and probably you heard about it, if you zoom, I would have a very big microscope and you zoom in very tiny, things start moving. So things are not fixed anymore. And this gives a lot of very interesting problems. And the logic of the quantum world is completely different than our own everyday logic. And then on the other hand, of course, we have the theory of general relativity, GR. It dates from 1915 with the publication of Einstein. This is the theory of Einstein. And that describes everything that is or very heavy, or that moves super, super fast. So if you want to describe a light particle, that's a photon. We have all in our studios a lot of photons going on. You need GR to describe them. But if you have something that's very small and very heavy, where a lot of mass is concentrated in a very tiny point in space, or space-time as it's called in GR, then you need the two theories together. And an example of such a situation is a black hole. So what is basically a black hole? A black hole is the process when you have mass and you would compress it you would be a giant, for example, and you could compress the Earth to the size of an how is it called? It's 0.8 centimeters. You can compare it to a little fruit, or then mathematically it will disappear and it will create a little black hole with a diameter of 0.8 centimeter. And the thing is, the black hole, so it has it's defined in one point in space-time or in space, where there's a sort of a lot of mass in a super tiny region. So it has a high density of mass, but it's very tiny. Mathematically it's infinitely small. And to describe what's going on in this region, you need quantum physics and GR, general relativity, and no one up to now. And that's a super big problem in physics. So it's been around over, I think, 100 years. This problem, or almost 100 years now. So and superstring theory, to make the connection, was I don't know, physicists gonna shoot me now, or I don't know, was a very good candidate to find a new theory for, we call it quantum gravity, to have those two theories together. And my PhD was situated in the mathematical part, so I had to do a sort of you could say, a classification. So if you look at general relativity, the theory of Einstein, it was built around a lot of geometry. So it's all geometrical surfaces. So if you study it mathematically, and the geometry was developed by Riemann in the 20th century, a mathematician, and he studied all those geometrical structures. Now, superstring theory is a generalization of general relativity. So you have, again, some sort of geometrical structures that are at the foundation. And the work in my PhD was to classify. I worked at the program to classify all those geometrical structures. And it was super fascinating because these were geometrical structures which had an infinite amount of dimensions. So here, we're sitting here in my room. I have 3 dimensions. You have 3 dimensions. In GR, we have 4 because we have time. Time is also an extra dimension. But in the geometries that I was studying, it was like infinitely many. So, I finished my PhD in 2005. So then I left mathematics. Because I got interested in the problem of quantum gravity when I was, I think, as a teenager. I don't know. I just got into the library and I started reading books and I got into the whole quantum physics. I was also very attracted to mathematics. So I had a dream that, like, maybe one day if I could work in this field, that would be amazing. But of course, I was also doing music. So it's always these two devils or angels, how you would call them. And then after my PhD in 2001, I decided to try to combine my interest for mathematics and music. So put a little bit the music more at the forefront. And then I lost a little bit the idea of applying my research of my PhD and the knowledge that I could gain for musical purposes. And now it got back because of the Black Hole album. So, and this Mikromedas was really the start, because with the first series, it was not so mathematical. I mean, it was a lot about also algorithmic composition techniques, so using Maximus P, pure data, to program new software, to turn those numbers using data sonification into sounds. But now with the black hole piece, it was also a question for me. It was a challenge that I put myself. Is it possible? I mean, because I had the idea, I think in 2016, I had to play a gig in Berlin with friends in Berlin for a collective. They did a very nice piece. It was classic music goes deep space. So I had to play with my piece, and then there was a wonderful classical ensemble playing classical music related to space. And it was a whole bunch super inspiring people over there. And yeah, this is also where I got the idea of the black holes. Maybe do something with black holes, and we're like, maybe yes or no, or it was a little bit, is it going to be possible or not? And then I said, okay, I'm going to try to see if I can understand the physics, because I was out so long, since 2001. Of course, I've been working since a data scientist as of 2005. But that's another kind of mathematics. I mean, yeah, that's more applied mathematics. You have pure mathematics, applied mathematics. And I think the start was going to a conference on black hole astrophysics in Frankfurt at the High Energy Physics Institute. The exact name I have to... and there it was a real eye-opener because I studied a little bit, again, the mathematics. I had to study a little bit of GR and a little bit looking at quantum physics. And there I saw a lot of it. Well, I was really completely again into this beautiful world that also is very imaginative. I mean, it's a lot about imagination. I still remember going to the talks at this conference on black hole astrophysics. And then typically the people who would give the talks, the scientists, so the scientists, they give their or her talk. And then at the end, somebody from the audience would ask the question, but is it physical? And in the beginning, I was like, okay, what are they asking? And at the end of the conference, I knew that the question, if they ask this question, they wanted to ask, but does it have something to do with reality, what you're telling here? And then the scientist would say, yes, maybe, or no, or... You see, I mean, it's a lot about... It becomes like science fiction, but real scientific science fiction. So, and this got me really inspired. So I thought, okay, maybe there's things you can do there because, of course, I didn't know how hard it would be to get the data out of it. And then it lingered on a little bit. And then it really started because of Concertgebouw Brugge. That's a concert venue. It's a very big concert venue for classical music in the region. They decided to co-produce the whole piece. And they also got me in touch with some scientists. And also because of going to the conference, I already had some really good contacts with people, including, for example, Dr. Matthias Kaminski. He's from the Alabama State University of Alabama. And together with his student, Casey Cartwright, they are specialized into researching what happens if you basically generate black holes in parallel universes. This again relates to string theory, because in string theory, we have 4 dimensions. So that's Einstein said there's 4 dimensions. But then the people in string theory said, no, there is 23 dimensions in the first version. So people are like, okay. But they have a very clever way in getting away with 23 dimensions because they say there's 4 observable dimensions at the macroscopic level. And then there's 19 dimensions, and they're curled up in tiny little microscopic dimensions, so we don't see them. So, and then the later versions had like, I think, 10 dimensions, I think, if I'm not wrong. And the group of Kaminski, they use this aspect to generate black holes in parallel universes. And then they perturb the black holes. What does it mean to perturb them? They disturb them a little bit. They throw a couple of planets into the black holes, and whenever a black hole you throw matter into a black hole, it's like a burp that it gives, and this is the famous gravitational waves that come out. And then the gravitational waves are the only messenger particles, only way to communicate between our universe and a parallel universe. So, and what they then do is then they see how these gravitational waves enter our universe, and this is the data that they give me. So, but to give you a little bit an idea, it's a lot about image because it's like you're talking. I mean, this is not so everyday way of thinking, but it's very interesting to see that. I mean, a lot of research is and it makes sense, and we can probably do things with it. More than we initially think. So,
well, it's definitely difficult to imagine any other dimensions of perception. I think if we lived in a 2D world, to imagine that there was a third dimension would, be almost impossible. And so this imagining of 19 additional ones is... I think I'm going to have to just accept that I'm not going to understand that anytime soon.
No, but no one. I mean, it's not an.
It's all theoretical, right?
It's theoretical, but as of now, I mean, there's a lot of observations that are being done or that are planned to try to figure out if it is true or not. There is ways to try to figure out if there's extra dimensions or not. One way would be to, and that's what they tried to discover in CERN, so the Large Hadron Collider, so these particle accelerators. One of the research programs, but I read that, I mean, they didn't find it yet, is to try to find microscopic black holes. So those are tiny little black holes. And if they would exist, then this can be proof of maybe having extra dimensions. So that's one way. Other way I read was also studying, I think, gravitational waves that are being emitted by mergers of black holes or very, very heavy objects. Or also looking at other neutron stars, I thought might contain information about possible extra dimensions. I mean, it's not. I don't think it's because we're human. We only have our senses, but reality is so much more. We live we cannot go out of reality. That's the big problem, and that's an old philosophical problem. You cannot put yourself out of reality and look, it looks like that's not possible.
Right. We can't perceive things. We don't have the senses to pick up on.
But the nice thing is...
I believe... No, go ahead before I...
the nice thing is, of course, when going into the whole project, I also started to realize, because I didn't know it before, that, I mean, these crazy ideas like extra dimensions or time travel, that's another old classic idea. You can really put up some experiments and try to figure it out if it's possible or not, and that's crazy. So,
Do you think we can time travel?
Yes, of course. That's another. Yeah. Yes, and there's two ways, of course. If you yes. But maybe a little bit discouraging. So going into the future theoretically is not difficult. I mean, every theoretical physicist...
I guess we're always going into the future, right?
That's one thing.
Automatically.
But faster, to go faster. Right. I mean, every theoretical physicist...
You're in the future. You're about 5 or 6 hours ahead of me right now.
Yes. But I mean, that is the future because we have, as humans, a convention on the time zone, of course. Mm-hmm. That's a different... I mean, it's really about time, the real... I mean, the entity of time. And to go into the future faster, so if I would want to go faster or you want to go faster, for example, you want to see how would it be like with all the climate change things going on, it would be good to see in 100 years, hopefully everything is under control or not. A way to do that would be to take a spaceship, and a spaceship that travels very, very fast. You've probably heard about it, twin paradox.
Yes, with the one goes real fast. Two twins get on two separate spaceships. One goes really fast, and I forget exactly who comes back having aged, and I'll let you tell it.
It's like the person who's in the spaceship and the spaceship that moves very fast from Earth. Let's say it moves at 0.9 the speed of light. They come back. For them, time goes slower. Relative to our time. So if they have traveled 1 hour, they come back, and maybe on Earth 1,000 years have passed or more have passed. So that's one way. The other way is to find a neutron star or a black hole, to travel in the vicinity of a black hole or a neutron star, because there the gravitational forces are very strong. And the thing is, the more gravity you experience, the slower your personal time will go. And by personal time, I don't mean your personal experience time, but this is really the physical time that's attached to your world line. We call it a world line in physics. Everyone goes to space-time in a world line. And so if you would go with a spaceship in the vicinity of a black hole, you have to stay a little bit away because it's dangerous. You have the same situation because the gravity slows down time. So you stay there 1 hour, blah, blah, blah. You go back and 1 million years have passed on Earth. Perfectly possible. And this is also something, time at sea level goes slower than time in Mount Everest. That's also because of GR. It's tiny. It's very a fraction. But if we would not calculate those effects of GR into, for example, our cell phones, GPS will not work. So GPS has a relativistic correction for time to make it work. Yeah.
Whoa.
Yeah. This is one example of yeah.
So us people like here living in New York, close to the water, rushing around all the time, we're passing. That's why our lives go by fast. So if we were hanging out in the mountains,
but it's almost
so
unnoticed. I mean, you cannot. Yes, but theoretically, yes, that's the fact. Yeah.
But it does affect our perception of time in a way, right? Because like when we're busy, when we're moving fast, like time just flies.
That's another
our perceptual time.
Yes, that's another issue. Of course, I don't have a lot of. That's more psychology, and that's true. That's another the personal perception. Yes, that's another interesting. Yeah, I mean, for me, it's just from the physics point of view. I mean, because you can measure it using atomic clocks, or they do it with airplanes, and then I mean, you really see the effects of GR. I mean, but the big problem is, and that's Back to the Future, is going to the past, because of course, there, if you would go to the past, then you have the paradox, or you could kill your. I mean, it's not a nice thing to say, but you could kill your parents, for example. It's like what happens in Back to the Future.
Right.
And then a lot of things, problems arise. But there is a solution to the Einstein equations, and it gave rise to something which we call wormholes. I think they were discovered in 1916. I'm not pretty sure. It's called an Einstein-Rosen bridge. And those are connections you make between 2 points in space-time. So we have four-dimensional space-time. But then you even have it's something which you call hyperspace around space-time. And the Einstein-Rosen bridge connects a white hole. That's the reverse of a black hole to a black hole. And a white hole is something that pushes matter out at a very high velocity. You cannot go back in. And this makes it possible to travel into the past, theoretically. But the big problem with the wormholes is that if you just put one tiny little electron or a proton or an elementary particle into, so you create the wormhole theoretically, but you put something little into it, it collapses. It is the stability of the wormhole is the same as if I would try to put this pencil straight ahead onto my thumb. It's almost impossible because I mean, physically, I would have to be like a robot, and even then, it's the same problem that arises. But the good thing is that I think a year or a year and a half ago, there was a collaboration between Maldacena, so he's one of the most proficient physicists for the moment, working on problems related to quantum gravity, and a Chinese physicist, I think, I don't know his name anymore. They found a workaround to the fact that if you put a tiny element into the wormhole, it collapses. So they found a solution that maybe the wormhole could remain stable. And this gives possibilities to travel into the past. So, yeah, but this is all speculative, of course.
Yeah, of course. That's, yeah, I feel like I'm going to be sitting on the other end here saying, whoa, a lot.
No, it's not. That's not my, no, it's not mine. But it's just to give you a little bit an impression of the science fiction.
Imagination too. And
yes, yeah.
Now, if I understand black holes correctly, the gravity is so dense or so powerful that not even light can escape it, which is why it gets the name black hole.
Yes.
And I think for quite a while they were just theoretical.
Yes.
Until relatively recently, right?
Well,
had the proof. So
yeah.
I guess what I'm trying to figure out is they're so hard to observe. It must be hard to get the data for you in the music creation process.
Yes.
Or maybe there's breakthrough. I'm not sure, but I guess that presents a problem, right?
It's very interesting also. So the news about the new album, so it appeared on a lot of electronic music websites, so they took it all over. It was very nice, of course, but I didn't expect it. So it was, for example, DJ Mag, famous for the top 100 DJ kind of stuff. They put it on their website, and it was on Mixmag or Music Tech also. And then if you see the comments of the people, it's also you get this reaction that people say, but there is nothing coming out of a black hole. I mean, this is a hoax. I mean, it's not true. And I understand that, of course. Yes, it's a black hole, so nothing can come out. There's no information that comes out, and we only can observe the gravitational waves if we're lucky that two black holes meet and merge. But for the rest, I mean. Of course, if I say there's no information coming out, it's not exactly true, because that is what Hawking proved us, showed us with his work. So basically, Hawking and Bekenstein, they discovered that black holes, they have a temperature and they evaporate over time. And in the evaporation process, they emit information. So there's particles coming out, but very, very slowly. The thing is, if you have a black hole, they have different sizes and shapes. If you have a black hole that has the mass of the sun, for example, you can calculate the evaporation time, but it will be maybe longer than the whole existence of the universe. So it's just basically not possible.
Would they theoretically, if they're constantly pulling things into it through its gravitation, would it eventually
collapse everything?
You say it evaporates? Yeah, so I can say, wouldn't it eventually just pull everything into it? And
yes,
is this the Big Bang?
No, Big Crunch. So you could call it the Big Crunch.
The opposite of the Big Bang?
Or you have the theory that there's a Big Bang, and then it grows together again a Big Bang together. This is called the theory of multiverse theory. But the thing is, that's right what you say. There was a big problem in physics because black holes, before Stephen Hawking and Bekenstein, there was a problem with black holes because they would act as vacuum cleaners in space. So they would eat all the mass, and mass has structure. Mass can be a nebula, or a planet, or a star. It has something which we call an entropy in physics. That's a structure. And the more chaotic something is, the higher the entropy is. And things tend to evolve towards a high entropy. This is also classically, if I take this glass and I just drop it on the floor, so now it has a rather low entropy, because it has structure. It has a sort of a geometrical structure. And if I put it on the ground, the entropy rises because it's all shattered in little particles. So, I mean, there's more information about the glass, because now I can describe the glass with, if I know the height, if I know the diameter of this, and I know it's a glass, I can perfectly reconstruct it. And I know the thickness of the glass. So if I drop it, it's not the case. And black holes acted as a sort of a vacuum cleaners, because normally things in nature evolve towards a state of a higher entropy. That's called the second law of thermodynamics. You cannot go backwards, because otherwise it would mean that all the particles of the glass could, by magic, come together and form the glass again. Statistically, and from the point of quantum mechanics, it's always possible, but I have never, no one has ever experienced something like that. And because of black holes are like vacuum cleaners of space, they would lower the entropy of the universe. So this was a big problem, because you would violate the second law of thermodynamics, and as you say, you would make the universe very homogeneous and very low entropy state. But this is completely contradicting a very important law in physics. And this is what was so genius about the work of Bekenstein and of Hawking, that they proved, by proving that the black holes evaporate, this information, this chaos that they sucked in, they gave it back to the universe. So the problem of lowering the entropy in this way was solved. Yeah. So, And the thing about a lot of black holes, like pulling together and forming a super massive that's maybe one hypothetical, but that's very unlikely that it happens, of course. But now I think, because the first black hole was confirmed in 1971, it's Cygnus X, and it's a double star system. So I think it's a red giant. A red giant is like the sun. Our sun will become a red giant. It's something. The sun will blow up, basically, and then it will become very, very, very huge, but gas-like. And the companion of the double star system of Cygnus X, so it's a red giant swirling around another astrophysical object. And by doing calculations, this object was confirmed to be a black hole in 1971. So from that moment on, we know that they exist. And now it is thought that there's zillion and zillion black holes. The one in the center of our Milky Way is, I think, 40 million masses of the sun together. That's called a supermassive black hole. The biggest black holes are, I think, a couple of billion times the mass of the sun. So, but for the album, of course, this is a problem. So 2 comments I get is there's no sound in space, which is correct. And then,
I was going to ask.
Yes.
The Alien movie in space, no one can hear you scream.
Yes. That's the whole beautiful, you have all the very beautiful Star Wars sounds of I don't know how these spaceships, beautiful, The movie would
be a lot less exciting without that.
Yes, suppose, imagine without sound, it would be very boring. And there's no information coming out, no sound. And that you can solve using simulations. But of course, to work with those simulated data, I didn't do it all by myself. First, I'm not an expert in black hole astrophysics. And secondly, I don't have the computing power to calculate everything. So I had to collaborate. For example, one of the collaborators was the Center for Plasma Astrophysics at the Catholic University of Leuven. And what they're doing is they're trying to simulate, for example, what happens. You have a black hole in the center of a sort of a VR environment. You take a sun kind of object, and then you let this black hole devour this sun. How does it happen? And it turns out that a lot of the physics is physics that we knew from quite a long time ago. It's physics that's related to fluid dynamics. So the equations are very similar to trying to simulate what happens, for example, when you take 2 fluids and you pour them together. Very difficult mathematically, very beautiful, very difficult to... and for these simulations, they were simulated on a cluster computer. And so it means they hire, an afternoon or a day, computing power, but it means you have a computer at your disposal of, 20, 40,000 CPUs at the same time, in parallel, calculating. And what comes out is very beautiful. They got me the data. It's like a cube of 4096, 4096, all little blocks. And there you see every frame in time is like, I think it was 1 or 2 gigabytes of data. One time frame, and you get a couple of hundreds of time frames, and then there's software to render it in a sort of a 2D environment, and then you beautifully see the star completely being devoured by the black hole. But the lesson here is, of course, that you have to try to collaborate. That is something that you cannot do.
That's interesting that it creates recognizable shapes,
yes,
like you said, and very precise.
Yes.
It sort of speaks to some kind of connection, some kind of like universal law or something that is tying everything together.
Yes, of course.
Or is it the interpretation of the data that we're making it? Is that?
It's the mathematics that's behind it, because of course a lot of those simulations are governed by mathematical equations, and And those are equations that can be applied in different situations. Like the fluid dynamics with those fluid dynamic kind of equations. These are called Laplace equations for the mathematicians who are listening to the podcast, or physicists. They originally were used to simulate the behavior of fluids. So it's because you have a sort of a mathematical machinery that you can apply in different situations. So, for example, the origin of string theory. So string theory basically proposes that we think matter is built out of tiny little elementary particles like electrons, neutrons, quarks. But string theory says, no, there's even more fundamental particles, and they're not particles, but they're tiny little strings. And the only characteristic of the strings is they vibrate. And their only characteristic is how sturdy they are. That gives the property of the strings. But if you look at the mathematics of the string theory, it's all related to real world strings, like on a guitar. So I mean, it's a little bit more complicated than that, but it has a lot of connections to that. So it's again because we know the mathematics of vibrations, we know it very well. And then there were physicists in the start of string theory, and it originated from another field. I think it originated from the study of condensed matter physics, also a very interesting field that gives a lot of new ideas for theoretical physics. So it came from another field, and then people started thinking about those strings, applying the mathematics of vibrations that we know better and better, and then something new came out. So, yeah, so... I mean, this is a very musical theory, string theory, because, of course, it connects vibrations also.
Which is really all sound is. It's
yes, of course.
Particles moving in the air, really, right?
Yes.
I've heard the sense of hearing described really like the sense of touch. It's just moving particles touching those little pieces in those little tiny hairs in your ears, and in the eardrum, and it's actually the air moving physical touch, which is why we feel the bass in our chest when we go to like see a concert. And
and there you also feel, I think, physically the bass. That's but your ear, for example, there's also a very beautiful connection between your ear and we're talking here. Because of this is possible because of compression techniques of audio. Otherwise, we would not be able, and also our visuals are being compressed using MP3 or MPEG or other kind of codecs. And this is all based on Fourier Analysis. And Fourier Analysis is basically, it was, again, this mathematical discovery. I think it was 18th century Fourier. The discovery that that was a result. Every sound wave, you can find a fundamental wave in a sound wave, and it's composed of a fundamental wave and harmonic or inharmonic overtones if you put them together. And if you study the way how your ear works, your ear does a sort of an inverse Fourier transform in a natural way. So what will happen in your ear is that you have a sound, and your ear will do a sort of a spectrum. We all know Ableton, and we have spectrum in Ableton that you can see perfectly all the different... That's what's happening in your ear in a natural way, using the hairs that you say. And so there's the hairs that are moving. And the interpretation is just because of a neural network inside your brain that is interpreting. But the way that we work with digital audio, it's for me very fascinating because it is very inspired by how nature works. So, and it's maybe because, maybe as humans, we found a way to tap into how we work internally, not in a very conscious way, but there's a lot of similarities also there going on. So,
a whole universe inside the head.
Yes, and of course your eyes is the same principle. I mean, I have not such a big knowledge about how but it's a similar kind of working. And as you say, your sense, that I don't know. Yeah, is it also your sense? Like, sort of your taste, you mean, or your smell?
Yeah, I guess any of them, right? Like it's all gets interpreted and decoded. That happens in our brain, not really outside of it.
No. Yeah, but it seems like maybe because I don't like the whole New Age statement so much. Like everything is vibrations and it's all energy. And okay, it's true. I mean, but yeah, I'm a scientist also. But waves are very important. Yeah. So the sine wave or other kind of waves. And with the Black Hole album, sometimes, so I did collaborations. Sometimes I got software. That also happened. So there was a PhD student, Fabio Baccini. He gave me software to calculate behavior of different kind of particles near black holes. So if you throw a little electron and you shoot it with an electron gun in a certain angle with a certain speed, and what happens? How does it behave? And the black hole also can have different properties. So basically, a black hole, they say in physics, black holes have no hair. So there's a very funny name of the no hair theorem in black hole astrophysics. That's an official theorem.
Imagination.
The no hair theorem states that the only properties that are important to discern a black hole are its mass, so how heavy it is. It can have a charge, so it can have a sort of a load on it itself. And the third property is it can be spinning or non-spinning, and if it is spinning, it has something which we call an angular momentum. So that's the energy, the spinning energy. And those are the only three properties that a black hole has. So for the rest, it has no structure. So if you throw a whole building, if you throw a whole New York into the black hole that has a lot of structure and a lot of things going on, everything disappears. So the only thing that will happen is the black hole will have a little bit more mass. It can get a little bit of charge, more or less, and it can start spinning or not. That's the only thing. And this is also what was used in the software that I got from Fabio Baccini. You could simulate, like, if it's spinning like this, it has a mass, it's charged or not, and this all gives different kind of behavior. But this was software. I mean, that's it. It's his specialty. It's his PhD. I mean,
right?
Yeah.
You don't have an electron gun laying around that you can
No. I don't know if it even exists. I'm saying electron. I don't know. No. Or to see if it's correct or not. No. But of course, if you want to do that, and then I wear my hat again as a mathematician or a physicist, then you have to use a mathematical software. For example, use Octave or other kind of software packages to because it's not because you get a software script or Python that you get the data. So Fabio said, here is the script, you can use it. But then I wanted to generate, different kind of situations, and then I generated with software, mathematical software, I think 1,000, 2,000 different trajectories. So you can generate as many as you want. But that is something, of course, then I have to use my knowledge on mathematics and on coding to make that happen. And I read a little bit. Maybe I try to read a little bit the papers that Fabio has written about this. And I have a book here on black hole astrophysics, or several books now, with the whole mathematical. I mean, but you cannot in 1 year time know all the things like a PhD student. I mean, they're working 4 years non-stop. So I use a little bit my mathematical knowledge to the extent where I can use it, and if it's too specialized, it's always good to collaborate.
Now, maybe you can help me understand a little bit about how this data actually becomes music. Are you mapping specific values and information to, like, oscillators and
Yes.
pitches and how's that work?
That's one way to go
That
about.
must be a lot of your decision, I guess, right?
Yes.
Like this is where your creative part comes in.
Yes, absolutely correct. And I also see, so one of my big inspirations in music is Yannis Xenakis. Maybe you heard about him, a French-Greek composer. He did the Philips Pavilion in 1958 here in Belgium. I don't know if you know the Philips Pavilion. It's this futuristic kind of... it's one of the first multimedia installations built worldwide. It was commissioned by the World Exhibition 1958. And it was the architect... I forgot the name of a very famous architect. Yeah. Anyway, it was Xenakis was involved for the music together with Edgar Varese. And he used, so the strength of Xenakis is using really very deep mathematical theories and making something interesting with it. So he's also the founder, if you're interested, there's a book written in 1968, Musique formelle, formalized music. And if you read this book, everything that we're doing now, so we're talking here with the video and then the compression, it's at Ableton, the whole idea of Premiere, Ableton, all in this book in 1968. So this guy is like... and he's a big inspirational source because there's also papers written on his work. The process of devising the mathematical techniques and tools to make your composition is also part of the composition itself. So the distinction becomes absent. I mean, and of course, when I'm doing the album, the Black Hole album, it's an art science project. I mean, there's also science involved. And as you say, it's up to the composer to develop the techniques and the algorithms that they want to use for a certain purpose. And the more you develop such algorithms, the more you start to know, this probably will give this result, this will give this result. But I'm still also experimenting a lot. I'm also very into algorithmic composition techniques, of course, Max MSP. Lately, I've been diving a lot into jitter, so the whole visual aspects. For another project, I'm now into the area of OpenGL, GLSL as shader language, so that's 3D visuals. But I mean, this is part of the composition process. That's what I want to try to say. And that's your own decision. And with the Black Hole album, one way to use it, the data streams, indeed, is as you say, you take the data streams, numerical. You have to, of course, translate them because sometimes data streams might have values between 0 and 500,000. I mean, if you connect it to an oscillator in Ableton, it will not work. 500,000 hertz. So you have to scale them.
It makes sense because if everyone doing MIDI is doing this, basically, right? We have 0 to 127, which is not 500,000.
No.
0 to 127. Those are our notes. Those are our velocities. We can control every device you use that's sending MIDI is controlling things using those. That's our limitation. So it must be a lot about deciding what to limit, where to filter. I mean, that's what our minds do too, right? Like,
yes,
we can't pay attention to every single thing coming in at us. We'd be overwhelmed.
Yes, that's a very good point. Yes, indeed. Yeah, it's as you say. I never thought it's about using your own creative artistic filter. You're a sort of at the same time a curator and a producer of the sounds. For me, of course, the first step in doing an album, such as with the Black Hole piece, is creating your instruments that you want to use and a sort of a sample. It's not a sample. It's a whole set of different sound design. So that can be that you have a synthesizer such as Serum, for example, and you want to do certain kind of stuff with Serum, and you know your way around, or use this kind of wavetables. I've been using quite a lot of wavetables also in the album. And that's one set of sounds. And you might want to produce a track with those sounds. And then another set of sounds I also used that was also super interesting to try to figure out. There's a database of spectra of white dwarfs. So white dwarf is kind of a star bigger than the sun. So when at the end of its life cycle, it will so basically the fact that the sun star is stable is because of nuclear reactions inside of the sun. And how does it work? Well, you have a lot of mass. The sun is super lot of mass because of the theory of Einstein and Newton. Mass attracts. So normally, if there is no outer force, this gets smaller, small, and it vanishes into maybe a black hole. So you have to have something that compensates for the gravitational pull, and that's how the nuclear reactions come into play. Because if you push it closer and closer, things start heating up, and then at a certain level, there's a lot of helium and H2O, water kind of. It's a lot of helium. It starts to create nuclear reactions, and then the nuclear reactions creates an outer pressure. That's balancing the sun, because if you would not have the outer force, we would not be here. I mean, that's. And the thing is, in the nuclear reactions, helium, if you look at the table of Mendeleev, helium gets to an element of a higher mass. So that's there's the famous album or track of Moby, "We're All Made of Stars," or. That's really true, because I mean we are star children, all of us, because all the elements that make up our body are being produced inside the cores of a lot of stars, because otherwise there would be no life. Now at the end of its life cycle, so what happens is the sun has a lot of fuel, helium in the beginning. It gets more denser and heavier elements until it becomes iron. So all the elements that are left is iron, and iron cannot burn anymore. And then that's the moment when a star can collapse. And then depending on its mass, if it has enough mass, it will become a black hole. If it has not enough mass, it will become something which we call a neutron star, so super heavy. One spoonful of a neutron star is as heavy as the whole Himalaya. If it is a little bit less dense, then it will become a white dwarf. And a white dwarf is sort of there's a lot of electrons going on. Yeah.
I tell you, I'm going to have an experience tonight looking up at the stars.
Yes. Yeah.
It's so insane. Like, there's just no way to really comprehend it. But when you put it in like terms of like a spoonful is as heavy as the Himalayan.
Yes.
Okay.
Yes.
Even that is beyond my grasp, but it does put it into some sort of metaphor that I can understand a little bit.
Yes. And that I think is also important for the album to try to, I mean, I've been creating some visuals, but with the white dwarfs, the thing was so there's a whole database of, spectra of white dwarfs. So those are light waves, electromagnetic waves that are being recorded. But I was looking at those spectra, remember spectrum of Ableton, and the question I had was, as a musician, I mean, I'm also a regular musician and as a producer, can I just turn it into sound? Can I listen to the spectrum? So you have to find a way to make a sound that has the same spectrum as the spectra of the light waves. And in the beginning I was thinking, like, for example, then it's more like a scientific problem for me. Can I do it in max MSP? I was like, okay, I can use the Fourier theorem, so everything is built out of sine waves, but if I want to do it correctly, I would need a synthesizer with maybe 2,000, 3,000 oscillators. So I was like, okay, can that happen in max? Probably not, if someone knows. Now, I don't know but in the end, I used other software.
I have 3 oscillators over here you can borrow.
That's
about it.
But it's nice because I found a solution using R. It's a sort of a Python kind of programming. I know R because as a data scientist, I use R a lot. But I thought, it also has possibilities to do sound with it. I was like, I know it so well. So that was a solution to generate, and then with R, it's easy. For example, you have a database of, I don't know, it was 9,000 different spectrum, and with R you can program a whole script, and then you run it, and then you have all of a sudden a database of 5,000-6,000 samples classified on your hard drive. So yeah, I mean, but this was really connecting the idea of spectrum of Ableton, because we know, and then and this was also a decision of me, of course. Another person working with the data would have used it in a different way. I mean, there's so many, it's all new, this field. I have a little bit, I mean, it's not new, but it's a lot of unexplored territory. Yeah, I have the impression. It's super cool. It's like being in a spaceship, into unknown worlds sometimes. So, yeah.
But it seems like it has a lot of the core things we all do when we make music. We are making these creative, artistic filters, even by choosing a genre. We're saying we're gonna abide by these certain rules and these guidelines. Have you found any interesting connections with like the way the physical world works, the way the quantum physical world or the black hole physical world works, that maps out nicely with how music works, like music theory? Because music is so interesting, I guess, for you, I'm sure, especially you realize it's very mathematical. Yes. It's also very emotional, and it maps out so well to the physical world, and you can do calculations to come up with very musical sounds. Did you find anything that like lent itself well or created interesting musical patterns that made sense?
It forced me to go into, also as a sound design perspective, to start doing things that I would otherwise not do. So that's one thing, especially with the gravitational waves. And there was an interesting, because the work with the gravitational waves was a collaboration I had to do with Thomas Hertog. He's a physicist here from the Catholic University of Leuven. He's also, he worked a long time with Stephen Hawking, so that was nice that Concertgebouw put me into contact with him. And I had a meeting with Thomas, and then he said, I want you to do a symphony with gravitational waves. Because those are the closest connections I think we have with music and black holes, because the name says itself, gravitate waves. I mean, there's waves into, and you can listen to them. You told him in the beginning. But the thing is, I knew that, of course, the whooping sounds, but I mean, I'd make a whole symphony with those whoop. I was like, oh, that's not gonna work. I mean, it's never gonna work. How shit? Yeah, I have to solve this. And then Thomas told me that you can calculate those gravitational waves in a mathematical way. So there's also, again, simulations of mergers of black holes, and then the gravitational waves that come out. So it's a whole bunch of numbers. Again, just numbers. And with those numbers, you can calculate. I mean, those numbers are not the gravitational waves. With those numbers, you can calculate the gravitational waves. And Thomas said, "Okay, you can calculate it with those numbers." I was like, "Okay," but again, I'm not into the field, so I had to figure out, okay, the mathematics. All right, and then the solution appeared to be into generalizations of sine waves, and this was super cool. You had to use spherical harmonics, and those are three-dimensional generalizations of a sine wave oscillator. So, and using those spherical harmonics, you can calculate. So I could calculate the gravitational waves and look at them in 3 dimensions. So these are really evolving, beautiful 3-dimensional geometrical structures. But it's a sort of a generalization of the Ableton spectrum, you could say. So that was also for me like, okay, you have the musical thing, but apparently in those gravitational waves, there's a generalization of the whole. So that was, I think, one of the things that, I mean, that really came out nicely. Also, I mean, I learned a lot from that. And again, it's about symmetries, it's about waves, about vibrations. I think that's the common. Again, in quantum physics, you have the normal classical oscillator. So a classical oscillator is a spring. If you take a weight onto a spring and you let the spring move, this is called a classical a harmonic oscillation in physics. And there's physics. You can describe it with the physics. You have to use an equation, the constant of Hooke. Hooke was the enemy of Newton. It was discovered at that time. So this is Hooke's law to calculate it. But it is, of course, the same principle to describe a guitar string and the same principle to describe an oscillator in a synthesizer, because that's the digital version of this thing. And in quantum physics, there's again the quantum harmonic oscillator. And these oscillators then in the collaboration I did with Matthias Kaminski, they also had a sort of oscillators of the black holes oscillating whenever you threw matter into them, and they generated the gravitational waves. And they are, again, generalizations of a sort of a sine wave generator, you could say. So those vibrations are everywhere, and it's really strange, very strange, yeah. So I think maybe that's the New Age connection again, the vibrations. But the theory of music as we know it, with the overtones, because basically our Western musical theory is based on the principle of harmonic overtones. So you have a fundamental, then you have an octave, then you have a fifth, then you have an octave again, and etc. And by this you build the classical Western harmony. This is also something that you also find it in physics, and also in quantum physics, and even in black hole, because there's also in the theories on black holes and gravitational waves, you can find a fundamental frequency. You can find especially with the theory of Kaminski that he's working on. There's, I think, a first overtone, a second. There's some similarities there. Yeah. So there's so much things to do still there. Yeah,
it's beautiful, really, and just how interconnected everything is, and how even as tiny as we get, as large as we get, it's like all the same on some level, with same properties and interactions. I think that the black hole, the gravitational wave, if I remember correctly, was that little bloop we hear that they released. That's pitched up quite a bit.
Yes.
Right? Like the actual gravitational wave is like subhuman hearing.
Yes.
I don't know if it's like something like microhertz or maybe, I don't know what it is, but I know it was so extremely low. We would never hear it. We have to pitch it up to actually hear it.
Yeah. Yes. Yeah. It's also a gravitational wave. It's not like a sound wave, physically. What happens with a gravitational wave is it's a stretching. So you have the LIGO telescope. You probably heard about LIGO. The telescope with which they detected the gravitational wave. It's this L kind of figure. So basically it's here a laser. They shoot the lasers to the tubes, and then here there's two mirrors. And using those lasers, they can measure with interference of the laser, they can measure the movement in the arms. If the arm goes a little bit like this and goes a little bit like that. Because of gravitational effects of general relativity. Because in GR, normally there's also the factor, if you move very fast, you will become, I think it's taller or smaller, I forgot. Yeah, so, the length is also not absolute. And if the gravitational wave from far away goes to this L shape, what they are trying to detect is the movement and the very tiny little movements. And whenever there's a gravitational wave passing, they detect those movements. And then there's a whole, because I've read a book about the whole thing. This is also crazy how they, I think it's one of this, on a scientific level, we have, of course, CERN, the big particle accelerator. But I think the LIGO telescope is also one of the biggest achievements that we had in the beginning of the 21st century. This is like, they made like a telescope. It's the same challenge of trying to build a telescope on Earth to try to discern a 5-piece coin on the moon. That's the same situation. They solved it there. But you also see there's a lot of noise, huge amount of noise. So it's buried under a huge amount of noise, this gravitational wave data. And you need tons and tons of technology trying to filter out those noise. And it's a lot of digital, it's a field we call digital signal processing. But it's the same thing. I have here, for example, Universal Audio
DSP.
Twin. It's the same thing. It's the same problem. The Universal Audio plugins, I don't know how they work exactly, but I can imagine there's a lot of technology to beautifully emulate for example, I use a lot of reverbs from them on the album, not to make publicity, but most probably there's a lot of math going on, DSP going on to make it work.
Well, yeah, I guess like when you really, if you ever tried to I see you have some acoustic paneling in your room. When you try to play around with just a room,
yes,
trying to tame it or control the acoustics there's 100 million factors.
Yes.
And then you sit in your seat, and now you're another factor. Your body is affecting the sound. Everything interacts with everything else so much. I can't even imagine it. I'm glad there are people doing this stuff for us, so we can just plop the plugin in and just choose, okay, great hall, church,
yes,
cathedral.
of course, yes, of
and
course,
have something that takes us there. In talking to you, it's really like occurring to me even more so how amazingly delicate and fragile our universe is, our existence. Like you're just saying, the sun could just turn into a red giant, and that would mean certain doom for us all. And
that's gonna happen.
Everything. Yeah, thanks.
No.
Yeah. No, it's inevitable. I know. Soon enough, right? Not in our lifetimes, according to the plan, but everything is really delicate and in such a balance. And we were kind of talking a little bit before we started about data itself and how we've become so reliant on data and everything, even just, when we post a picture online and we're giving up so much data. And you were expressing some concerns about what this might mean for us. Because I think we're collecting it so fast and collecting so much of it so much more often. We're almost it's almost impossible to keep up with all of the implications and all of the possibilities and all of the potential dangers of that. And I'd love to hear for you to go in a little deeper about that stuff you were bringing up earlier.
Yeah,
before we started.
And as I said in the beginning, it's a little bit the backbone or the source to use data for artistic purposes. If you start using data for artistic purposes, you cannot get around the fact that the impact of data on our society and our everyday lives. And having now worked as over, I think, 15 years or as a data scientist, you see a lot of evolutions. And I think there's a lot of big challenges. As I said, there's the climate change problem, which is huge. We have to deal with it fast, hopefully. And besides that, there's the whole datafication of our society, and we have to be also the algorithms that are being more and more powerful and controlling our lives, which inherit a lot of possible dangers. I mean, yes, I've been reading a book. It's on data. They draw parallels between, and I also say it in the book, between the colonial history that we have in the West and in the US and the whole datafication movement of our society. I mean, it's not exactly the same. You cannot compare the whole colonial cruelty and that's not a... but there's some similarities because first of all, I mean, there's a whole problem that it seems like, and that's also written in the book, we have, of course, our ideas of a capitalist society and a free market society. But it seems like that's, of course, I think it's an interesting idea that everything is being turned into value. So we're trying to validate everything. And why do we try to validate everything? To be able to sell it, to have, again, a commerce around it. And we're now at such a point here in Europe, for example, or in the US or in Canada, or that people, I mean, we can buy a lot of things. I mean, still, not, but I mean, there's some possibilities. People, I mean, the thing is, the limit of people buying physical things is almost reached. I mean, of course, there's people who cannot afford, I know, and there's a lot of poverty. But the next thing, and that's the danger we have to be aware of, is the commodification of our social lives using data. And this means that our social relations become value. I mean, and we see that Facebook, I mean, Instagram, it all runs on this kind of ideology. And it is an ideology that's being imprinted. Okay, I'm a little bit before the generation of the whole internet boom and stuff like that. But younger people are really ingrained into this whole ideology of the commodification of your social lives. And this is very dangerous because it also will lead to a sort of a normalization of social interactions. So we will have less freedom. That's a very, very, very pertinent result of that. And another thing is, I mean, that's now what's now happening, and it's going to go further and further. And to give an example, in the world of data science, in the beginning, it was all about gathering data. That was like, first get the data. Then the next phase, and that's the phase where we're entering now, is to try to do predictive modeling, they call it. And in predictive modeling, you use the data to try to predict behavior, predict evolution of systems. But originally, those are elements that are coming from not from social sciences, but they're developed in a purely scientific, a hardcore scientific environment, being applied to social relations to human beings. And this is very dangerous because, for example, if you want to get a concrete example, you want to get a loan, for example, there's hope. Luckily, in the western part of Europe, it's coming slowly and slowly. But there's a lot of predictive modeling, and the predictive modeling will use certain kind of proxies. We call them proxies. And for example, for me, it could be for example, I identify as male. I have this kind of age, I'm living in this area, etc. I have this medical past, maybe. It's not possible yet, but let's wait for the future. And based on those numbers, I will have a sort of a credit score for an insurance company. And based on that, the insurance company will say, you can get, the bank will say to me, you can get this loan or that loan. The same with insurance companies. I mean, and it goes further and further. And this is all based on predictive, these predictive models. But the problem is that a lot of people don't realize it's only an approximation of reality. And the problem arises when these things are starting to replace reality. And then you're entering a sort of a Blade Runner world. And this is something that's slow. We have to be really aware of that. That is a big concern. And of course, you cannot avoid it. I'm also using Facebook, Instagram. I mean, So, but it also has connections to climate change, because using these predictive models, I mean, you can try to get false information to people. You can try to direct. I mean, what happened with Analytica, Britannia Analytica, with the whole elections, that was completely based trying to predict behavior using consumer models. I think they were using there was a campaign that also written in a book. The person responsible, for example, and that's then Obama. You would think Obama, okay, but the person responsible for his election campaign, he came from, I think, consumer marketing world, and then they started to again try to predict the behavior of people, what the reaction would be when they saw this or that kind of ad for the elections, and try to direct their behavior in a certain kind of a direction. I mean, you see this undermines a lot of free thinking. It undermines democracy. And it's, as you say, it's going faster and faster. And I'm not such a proponent of all those. I try to always make people aware of the limitations of those predictive models. I mean, it's pure statistics. There's always a chance that there is errors, but of course, it's very dangerous to. I mean, when you're doing data analysis and data analytics, there's the modeler. So first, there's noise on the data. The data is not correct. You cannot measure the data correctly. Then there's the models that are being used. There's error there. Then, as a data analyst, you have to communicate those your results to decision makers, to key persons who play a key role in communicating those results to a broader audience. It could also be to the board of directors of a company, but they all have their own political agendas, so it gets skewed. I mean, with numbers, you can twist and turn, and I think that's also what's worrying me is the whole Corona and COVID crisis. Is I understand it. I mean, people lost faith in science, but a part of it is because the communication about the results. Also here in Belgium, you had this and that, and all of a sudden, if you're not into the, I mean, yeah, if you know a little bit, and even then the statistical background, then you're okay. You can more or less sometimes navigate into it, but they messed it a little bit up. And now we have to try to restore this faith in science, and that's also what I want to try to do with the project. Science is not absolute. It's just a way to look at reality. It's not perfect. It's not a replacement of reality. And a field where you see that very well is the black hole world, because, hey, we're talking about 10 dimensions, 5 dimensions, 23. I mean, this is not reality. This is completely far off reality. But I want to try to make people aware that the same holds true with all mathematical models or predictive models that also have a direct effect on our society. Everything has to be viewed into context, and every model has its strengths and limitations. And if you take those two balanced into consideration, you can have better science, better communication, and I think better acceptance, and hopefully the reluctance on science will temper a little bit. So, but how to solve it, I don't know. I mean, that's and then the commodification. We have the commodification of our social lives, so that's a big problem. And also, we are working basically, and that's a very nice thought, of course. Capitalism, I mean, I'm not against capitalism completely, but I think it should be in balance. I think that now there's imbalances. Some things are like way out of control. Wall Street, and a lot of other things. But the commodification, we have our social lives, but the next step, and that's already worrying a lot. But the next step is going to be our internal bodily structures. they're going to want to commodify those using maybe nanotechnology. And I don't want to put any conspiracy theory that has nothing to do with that, but it's just a fact that the medical world will also be interested into maybe in the future putting a sort of a sensor in your body to sense all the different activities in your body. And based on that, again, calculate your premium for your insurance, calculate this and that. And we have to be it can have benefits, but you have to be very conscious about and also, like, for example, Elon Musk, when he says, I want to connect the brain to the internet or the brain to, okay, but I'm directly thinking, okay, but what are your motivations? I don't think your motivations are so noble. I can't believe it. I mean, imagine that we're all connected via a neurochip directly online, because I think this is one of the future ideas they have. What potential it has. I mean, then you're living in 1984. You even do not have your own thoughts anymore. I mean, so, I mean, this is maybe far-fetched, but the idea is already being officially proposed. And, I mean, it's not that Elon Musk is completely considered as a complete crazy clown when he says this. There's people like, yeah, okay, and...
Yeah. Well, I know, he feels the connection from our devices as a bandwidth limitation that we can eliminate with this connection. And I think, it's interesting because we've done it socially, right? And now you got, everyone has crazy Uncle Joe who at Thanksgiving dinner or, at the Sunday dinner will say his outrageous things, but it stays at the table. But now crazy Uncle Joe has the platform to reach the world. And these are maybe ideas that shouldn't have really seen the light of day like they do. But if I understand correctly, and this is really an interesting point, it's something I haven't really thought about so clearly, but you're saying we got the data, right? And we've always heard phrases like the data doesn't lie, the numbers don't lie, things like that. But we have, after we get those numbers, we have somebody that needs to interpret them.
Yes.
And then communicate them to someone else who then needs to implement them somewhere else. So there's a lot of points of failure. And what I guess we're seeing a lot in our world with the lack of faith in the data and the science is really more the failure from the interpretation, from the communication. And then, of course, you can selectively take the parts you want for your own means to paint the picture you want the people to see.
Yes. And that is the principle. When you don't say something, you don't lie.
Right. I didn't lie. I didn't tell you the key fact that you needed to know, but I didn't lie.
But
it's interesting what you say about how we can start giving ourselves these credit scores. And I love that show Black Mirror that comes on Netflix. And there was an episode where they had a phone type device, but they also had some sort of visual screen in their head.
Okay.
And every time they went up to somebody, they could see their score. And you interact. We have this nice conversation. I give you your 5 stars when you're done. You give me 5 stars. We had a great time. But maybe I go to the gas station and I get a 4 for some reason. I wasn't nice enough, or where we can start doing that. And because I think we really want a society where we're pushing a lot towards getting rid of our judgments of each other. We don't want to.
Yes.
We want to see each other as individuals and who they are. But if we start moving in that direction, we're making snap judgments. We're saying, okay, you were in. I didn't have a good interaction with you on the elevator, so screw you. I've totally judged you on the tiniest slice of your life, the tiniest moment. So that could be kind of scary, because that's exactly what we don't want. We want to see each other past, the initial impression, and to take into consideration the full picture of who we are.
That's the reverse. It's contradicting each other. I mean, but it's interesting you say that the credit scoring system that you propose, and it already exists. For example, Yelp, or you just go to Uber. Yeah, of course. All those funny movies. The SNL. I really love the SNL comedy movie clips. There's also a lot of movie clips about about Uber. Jenny from Uber, they completely left the whole system. But yeah, I mean, yes, of course, that's a sort of a scoring towards each other. But then on top of that, there's the credit scoring systems that are being generated by you without your knowledge, using predictive modeling, and you have no control over that. So if you're in a bad situation, you're just basically screwed. And there's examples of... there's examples in the book that I mentioned about the data colonialism, about a teacher. I think she got a bad rating score by an algorithm or another, and she really had to go to court to change it because it prevented her from getting a good job, for example. So that's the other thing. And if you're talking about those automatic scoring system, that's the credit scoring system. China runs on that now. This is the whole thing. In China, it's being implemented. So this is not science fiction anymore. This is a reality there. So based on your credit score in China, you are allowed to have this amount of children. You are allowed to have this kind of car. You are allowed to send your children to this kind of schools, not to those schools. So this is already being implemented in China. And I don't say, I mean, this whole system is going to come over to here, the other... But it's a sort of a light version, and not such a light. I mean, there's a modified version, and this modified version, because officially China is communist, but this version is being implemented by a sort of neoliberal, datafied vision on society. And this is what I see also as a data scientist, and this is what really freaks me out. It's I think I mean.
Well, right. I guess, if you're getting analyzed for, say, you need a loan to help you get into a better position in your life, and I'm the bank, and I say, well Valery, according to the predictors here, you're a risky candidate.
Yes.
So, sorry, man. And you're stuck. And
yes.
Then, someone else comes along who fits for whatever reason, they just... So I could see this like further dividing people.
Yes, I mean
it's
not working against, for example, discrimination. For example, there's also an example. Suppose there's a neighborhood somewhere, a bad neighborhood. You have a zip code, so there's a person living into this neighborhood with a zip code attached to, this person has more difficulty to get a loan. For example, if she wants to get a loan, she has to pay more money. Because living in that area, there's also more policing, but because the policing is also predictively modeled. Because of the predicted policing, there's more chance of being arrested. If she gets arrested because of some demeanor or whatever, or even nothing, that also happens a lot. There's more frisking, for example, in such areas. Because her friends are also have more a chance to be frisked. If she gets to a court... There's also some predictive modeling now in the US being involved into the legal department. She will have a more chance to be convicted because of a crime that maybe she has nothing to do with. So, and then you get into a sort of a spiraling situation that is not beneficial for this whole community. It drags this community even in a worse situation than it already was, and it divides and it discriminates against these discrimination becomes worse and worse. So it's not helping them. So, and as you say, it has a potential of leveraging the differences in. And there's several reasons, of course, why this happens, and there's solutions for that, of course. I mean, but there's political solutions, there's technological solutions. And there's also the problem of the underrepresentation of those people and the people who are developing the technology. That's also something that we know already a long time. But I think, this...
It moves so fast. We don't get to see the results of it until we're already, 10 times further down the hole than we were. And
yes.
We're really we're becoming aware of how our social media is affecting us. We're seeing the division between people. We're seeing people's self-esteem and mental health suffer.
Yes.
But but we're so far into who's going to give up their account? Who's going to...
Yeah.
It's like we know it's destroying us, but we can't put it down.
Yeah,
it's
but
become too much of our life.
That's
we
true.
rely on it too heavily.
That's true. Yeah, no. I mean, if you're as an artist, if you don't connect to Facebook or no social media at all, I think it's not so easy. Yeah. So, but I think there's some certain kind of limits, boundaries that I hope that people will really resist. And that one of the boundaries would be, the predictive modeling, if that goes further and further, I hope sooner or later people will say, okay, this is not acceptable anymore. And the other thing is, of course, if they want to implement the commodification of your internal bodily structure with sensors inside your body and stuff. I mean, that for me would be a no. I mean, I would... Yeah, I mean...
I've asked this question to my high school students. They're young. They're kids that have never known the world without an iPhone. They're born probably about the same year the iPhone was born, So that's just all they know. And I think I'm seeing more and more. I'm like, yeah, put it in me, I can watch YouTube while I'm sitting here pretending to listen to you. Sure. I can do. There's so many, I don't think it's just kids though, because I think we're going to see things like, this can tell if you're going to have a heart attack. This can tell you if you're going to, and we're going to say, well, man,
yes,
if I would have had this, or thanks to this thing, I'm not dead.
Yes, no, that's the other thing. Yeah, no, that's correct. Yes.
It's
difficult.
Weird. There's so many possible really great things.
Yeah, it's the same with music. Yeah, with music and artificial intelligence. This is another field. I've been working on in 2007. I worked on a project called Emosynth, and with that project, it was with a little team. We realized a prototype of a system that can automatically generate music, and the music adapts itself to your emotional reactions using biofeedback and using genetic programming. So that's AI.
Wait. Let me just make sure I understood you.
Yeah. Yes.
The music will pick up on your biofeedback. So was that like your heart rate, your
stress
body
level,
temperature,
stress and heart rate, because they're all correlated to each other. Yeah.
And it'll be like, all right, let's make him feel more calm, or give him the energy burst he needs.
Yes, that's
Really?
Yeah. And the idea was, what we did was, you could use the system to automatically generate a personalized soundtrack for a movie with a maximal emotional impact, because the music is personalized, especially made for you.
Oh, so for each viewer.
Yeah, different music.
So I get a different soundtrack than you.
Yes.
That'll reach me. Wow.
Yeah, because maybe you hate violence, in whatever, and then this thing is going to be, okay, I have to do this and that. Yeah, but it was a prototype. I mean, it was a lot of programming and but working in that field. So what I basically had to do was make a sort of an automatic songwriter. An automized songwriter, and it was written in C++ and C#. Yeah. So, but with that, I mean, it was with a little team. I had a programmer, luckily a professional programmer, because I can program C++, but I'm not a seasoned. This is again another specialty. But I still remember when we had the first prototypes of the software, I could say, okay, generate and 5,000 songs. Like, yeah, I mean, this is just software, and then you can listen. But
in a way that we do use music a lot to fit our mood and our emotion. If I say I want to go to the gym, I want music that's going to... So instead of having to search through playlists and albums and skip the songs that are the ballads.
Yes. And this idea has not... I mean, because I know that Spotify and other providers are trying to make certain kind of algorithms to... But our idea, well, what I had went much further, I think. But of course, the implementation was primary and it was a prototype. But it got me thinking, like, part of the future. And we also, for example, there's a merger between Native Instruments and Isotope, which is super great. You heard probably about it. The two companies merged together. Isotope, I mean, is amazing. The AI that is in Isotope, I'm like, whoa, this is really amazing. So we'll see what comes out. But I think the potential for AI and music is going to be... In the future, there's going to be radio channels that are completely driven by AI. Yeah. There's going to be songs that, I mean, the only thing that's still... so songwriting is rather... You can do some quite good songwriting using artificial intelligence. But of course, we have our studios here. The production is more difficult. To have like a 60 different track mix using AI... But in 10 years' time, I think it's gonna be a reality. Yeah? So, and this is gonna put musicians in a completely different perspective, and we're gonna have to maybe reinvent a little bit of the things that we were doing. I don't believe that the human creativity and creative intelligence and the inspiration. I mean, I don't believe that a machine can replace a human being. No way. I mean, and there's mathematical reasons for that. But a part of our tasks will be replaced. I think, and there's a lot of producers who don't realize it or don't want to realize it, or don't believe it. And that's another aspect. I think it's interesting to see how that will. I mean, I mean,
there is something, it is. Yeah, I agree with you. Like I've already heard music that was, artificially created, and you're kind of like, you can see the writing on the wall. We're getting there fast too. It might have to be like just, I don't know. Maybe we'll get like more excited about different things, like just seeing somebody playing their guitar.
Yes, that could be. Yes,
just like I had my band practice last night, and that's just 3 guys, bass, guitar, drums, some microphones to sing on, and the freedom in that is great. But to think it's not coming, I think. I mean, how could you say that anymore about anything, really?
Yes, maybe, yes.
Maybe I need to move to that mountaintop with my acoustic guitar so I can experience life a little slower and
of course, yes, of course. No.
Slow time down.
But it's not that I don't believe in musicianship. I mean, I'm also. I mean, one of my big inspirations. I studied jazz piano and already for a long time. I played piano for a long time, and I listen. One of my inspirations, like Miles Davis, Coltrane, for example, Monk. I mean, Bill Evans. I'm a very big Bill Evans. So those are also very big inspirations for me because of the organic element and their creativity. I mean, this is like next level, and this is super analog. So, no. But I mean, AI is gonna be, it's gonna be a factor. That's that's going to be there. Yeah.
Yeah, and I think for creating that mood, if it depends, it depends, like, right? Like, people use music for different things, and some people just want the beat when they're partying with their friends.
Yeah.
And no judgment, that's
No,
fine.
yes,
And
that's true.
I use music like that sometimes too. I just want something to fall asleep to or dance with my friends for. It's very different than when I'm feeling introspective and, all the different things. But where I think a unique segment of the population as music creators too, that we do see it differently. So, and it would be just, I'm sure you could say this about any type of art, film, like I definitely do not appreciate film on the level of a filmmaker. I just don't even understand how deep it goes.
Yes.
Just as, so like I might be happy to just consume the mainstream simple thing because I want to just have a nice evening, sit on the couch and just relax. I'm not there for the intellectual, artistic experience as much as I am with music, maybe.
And then it could be nice if there's an AI engine, for example, that's generating a whole movie for you, because that will also be a possibility in the future. I mean, or different plots, one of my dreams is to have like I'm also a little bit of a horror movie fan. I'm still waiting for with holograms, 3D holograms, like a zombie movie, like Day of the Dead or something like that. Really with 3D holograms, surround sound, smell, everything, and then in your room, like. But yeah, we have to wait for that.
And you want that to happen?
No, now I'm just curious
by zombie holograms.
Curious how that would be. If you would your human condition.
Well, like the virtual reality, right?
Yes.
Hey, in a way, I was kind of laughing to myself when you were talking about scientists in virtual reality making these red giants, red dwarfs,
red giants.
They're simulating these in VR. I'm picturing a kid playing Grand Theft Auto, stealing cars and like shooting people for no reason, and now the scientist is destroying the entire solar system.
Yes, of course.
Step up.
Next step to Yes.
We got bored stealing cars in the video game, so now we're destroying entire solar systems.
Yes. No. But the red giant phase, you can check it up. I don't know. It's in a couple of billions of years that it will happen. Yeah. So we have to escape. I mean, that's true. So, I mean, that's where the people who want to go in space are right. We have to escape.
No sunblock for that. Just get out.
No. Because it's there will be. I think might be a white dwarf that's going to be left over. Then I'm not sure. I should check the literature. But it's going to be much hotter here. Eh? So it's going to expand, and the temperature is going to rise. So everything is going to it's going to burn. I mean, unless we are we have to get out. But personally, I'm very interested into time travel myself. So, the whole wormhole thing is very interesting. So, that would be...
Well, that would be interesting, right? Because then we could figure out if our solutions to our problems are working or making them worse. And we come back here and say, all right, we better not do that.
Yeah, you can see for climate change, you can go 100 years and then measure the temperature and then say, okay.
Ooh, that was a bad idea.
It has risen 3 degrees. Things like Belgium doesn't exist anymore.
Well, let me ask you this. If we can you said we can get into the future, would we be able to get back, though? To say, hey, guys.
No, not right now, because then you would need a wormhole. No, but it's all theory, yeah? So to go into the future, I mean, because if you read those papers, then, I mean, then it's like, okay, another idea, that's a super cool idea, is to use black holes as a driver for a spaceship. That's also possible. So there's several possibilities to make spaceships, and one of because you need a lot of fuel to go very far away, and a black hole's small
for the energy.
Yeah. But this is all. I mean, if you read, I mean, those are real scientific research. So, I mean, it's based on real science. But then, I mean, you have the ideas or sentences like, okay, let's take mass, let's create a black hole, let's try to move the black hole to a place where, I mean, this is all theory, of course. But okay, who would have thought
could it be possible to create those, like a black hole for energy in one of these like colliders, and use that to get rid of our dependence on fossil fuels and things like that?
The problem with little black holes, so that's again the theory of
the whole world into it.
No, that's one thing that can happen statistically. So there was protests in the beginning in CERN, people protesting against the fact that would happen. But the other thing is, the problem is, and that's again Hawking-Bekenstein, the smaller the black hole, the shorter it lives. So a very tiny, minuscule black hole would exist only for, let's say, I would say something 10 to the minus 20 seconds or something like that. So it's directly gone. You cannot, that's a little bit, you cannot make like sort of it's not matter, you cannot hold it. That's the problem with those things. They exist for a very, very short amount of time. But that's with other particles. If you look at the data from CERN, there's a lot of exotic particles that are being created, but they're not an abundance in nature, just because kaons are, for example, muons, but they exist a very, very tiny fraction of a second. But the microscopic, of course, the microscopic world works on another time frame than our world. And the macroscopic world again works on another time frame, because 1 year for the existence of our solar system is really nothing. Or for the Milky Way, for example, it's so. But maybe, I don't, but time travel, I think, we have to, maybe look into it. Maybe not in our lab, but if you look at radioactivity, for example, the applications, when it was first discovered by Marie Curie, she knew the potential, but how did it? Einstein, the discovery of the famous formula ESMC squared. Normally, there's some extra terms. It's given us all the nuclear energy, but it's given us smartphones. A whole computer is based on. It's also, and quantum physics the same. Quantum physics was discovered in the beginning of the 19th century. Okay, it took 100 years. Yeah, but without quantum physics, we would not have a computer. It's just not because we don't understand how electrons behave. To make microscopic electronica, you need a lot of quantum physics. So, we would not have all the synthesizers, plugins, Ableton. Nothing of that. Only a plain old acoustic guitar and a double bass and a drum and a vocal.
Which isn't too bad.
Which is also cool, of course. Yes.
Yeah.
No. Yes.
Well, that's wild. And who's to think that there might just be some discovery around the corner that will take us on a whole other road.
Yes, also possible.
For good or evil, but hopefully we'll use that well. Are you optimistic about the future? How do you feel?
Mixed feelings. I'm looking forward for, of course, the progress in technology and science. But as I said, the dark side, I'm worrying about, of course, the climate change. This is something, and the datafication and the implications. But I don't think it's too late. I'm not how you call it, I think we can. I'm nihilist. No, I think we're humans, but also as to climate change, I don't believe in geoengineering. There's people who really say, okay, in the beginning they denied the climate change. Now they say, oh yes, it's happening, and we're going to geoengineer the Earth. That's another solution, to try to put mirrors there, or put, for example, in Saudi Arabia or in Dubai, I read they have a technique to make it rain over there using technology. But of course, the Earth is an ecosystem, and you cannot. I mean, this is crazy.
Yeah.
So
one thing affects everything else.
But I think we have to get out. Of course, we have the corona, which was also and still here and there over everywhere. That's of course another challenge. Yeah, that's another challenge that's being put. The other problems a little bit. Okay, now there's the convention on the climate change in where is it, in Scotland or in Dublin or going on?
Yeah, I think maybe Glasgow.
Sorry, Glasgow. Yeah, so it puts it in the picture again, but hopefully it will not be forgotten. So optimistic, pessimistic. Yeah, but in between the two, I think. Yeah, but I believe we can do a lot, and I mean, and good. I mean, yeah, awareness. I think the most important thing is awareness, and to try to convince people. And I do it maybe in a naive way with science, but yeah.
Well, it's cool. And look, I'm having this conversation with you on the Music Production Podcast.
Yes.
Which is definitely, this type of science is not happened yet on the show.
No.
That's something I love about doing it and talking to all kinds of people, and someone like yourself, is that we can go down different wormholes to use a pun for you. But we get a chance to connect it all and learn about other things. And, through my study of music, it's taken me in so many different directions. And I find all this stuff fascinating. And I think it's, extremely important for everyone to consider, kind of like the small role we all play in the bigger picture.
Mm-hmm.
Because we're kind of like atoms in some larger thing.
Yeah.
Each one of us bouncing around, affecting each other, and changing our charges from positive to negative.
Yeah. Yes. Yeah.
So I like it, and I think what you're doing is really awesome and impressive, and we should definitely tell people to check out the music.
Yes.
Mikromedas is how you say it.
Yeah.
Mikromedas.
So Mikromedas. The title is Mikromedas ADS CFT 001, and it's being released on the label, because I said Ash International, which is part of the Touch label, and you can now already pre-order via the Bandcamp of Ash International, and the official release date is the 3rd of December. So it might be a Christmas present. It's going to be released as a digital download, as a CD also. So, yes.
A great Christmas present for someone that's into both music and science and astronomy.
Yes, that could be, Yeah. Of course.
No, it's very interesting and, of course, mysterious as well. But to know that the sounds you're hearing have a direct connection to aspects of the universe makes it really interesting and fun, and in a way it has this kind of earthly feeling about it too, where we recognize some of the sounds, and I like it a lot. And it's,
thank you.
It's just another way we can make music, and just when you think you've run out of ideas, and I've done all those chord progressions, and it's a great reminder to myself, to everyone, to just keep those eyes open, those ears open for interesting ways to create.
Yeah. Of course, we haven't talked too much about music production, but that's also the other side, but that's because it's not because I'm doing this, as I say, normally I came from another field, really musical, melodic kind of stuff. And I also use that in this album. Yeah. I was also working a little bit in the dance music industry. So I also did vocals. So I'm a singer. normally, but now with the whole album, not for the moment.
Well, you did mention, and I wanted to say this earlier, but I
yeah.
forgot. You did mention you studied like pop music, electronic pop music.
Yes.
That's not what this is.
No, this is not electronic pop music. No, not at all. Yeah, but I teach at the conservatory here, so I teach on electronic music production and sound synthesis and sound design. Mm-hmm. But I mean, to make the album, that's what I think I combined. My background there is, so I had all compositions, blah blah blah. And then I went to the studio and I was like, yes, and now I'm going to use all the plugins and I have a little bit of hardware and to really make the sound like optimal as possible. Like I was like, I think I mixed over a year, not constantly, but mixing better and better and trying to make it better and better and better. So, and it paid off. I mean, I also got new plugins, and then with this Universal Audio, I got also Plugin Alliance. I mean, using a whole bunch of different plugins to really, the idea to try to get a sort of an analog feel into the sound. That was for me like, I have some references, some records that I really like a lot. And I mean, I want to try to get a little bit in that direction. So because I can also be very passionate and intrigued by good, maybe very commercial pop music. When I listen to it and the sound is like, I'm like, whoa, how did they mix this or produce this or the vocal licks or like, so, and that's what I combined, I think, in the record. Yeah. So, because I also like it a lot. I also like pop music a lot. I mean, so yeah, and the album was mastered. That's maybe a nice and interesting detail. It was mastered, and thank you to Simon Scott. He mastered the album, and Simon Scott is also he has a company called SPS Mastering, but he's also the drummer of the band Slowdive, the shoegaze band.
Yeah, I saw that. That's pretty awesome.
And it was cool when, so I was like, yeah, all right. Simon is gonna, I was like a little bit impressed, or how you call it. I was like, okay, I'm gonna send the album over. I hope he likes it because Slowdive, you know, it's like a legendary band. And then I got a reply. He really liked it a lot. So I was like, okay, whew. I mean, already one person that's like, yeah. So that was really nice to hear.
Yeah, a much different style. than
Yes,
ever was.
Yes, yeah, of course. Yes. But Simon also makes very nice experimental electronic music. And I understand by the record label. And so Touch is that's Mike Harding, why they said, Simon can do the mastering. It completely it was a very good fit. So, yeah. And in meanwhile, yeah, of course, Slowdive, yeah. Yeah, so it's an amazing band.
It's fantastic work, and congratulations on the upcoming release, all the hard work and energy. I mean, you really put a lot into it, and a lot of interesting collaborations. And it's pretty cool to see how it just takes so many different aspects of your life and your interest and puts it into this artistic project.
Thank you, yeah. That
was inspiring.
That was the idea of and yeah, I think it's naturally evolved. It was not like, that was a little bit the problem when I was working more into the dance music community. Before I was felt more pushed towards like, it has to sound like this, it has to do, and with this project I was like, okay, naturally, and it could be after this experience, I have a follow-up record already ready. That's using the same kind of techniques, not data, but the same kind of sound design combined with more musical elements. And in the future, I do not exclude that I will even go more in a musical direction, or maybe do some dance music again with the new ideas and techniques that I now discovered. That's a little bit. But we have to
now you've given yourself a whole nother palette and set of tools
for
any style that you want to pursue.
Yes.
That's how I feel too when I go into another world musically. Then it's like I can come back to some of my older roots and I'm fresh again.
Your roots are in where are your roots lying musically?
Like just rock guitar and alternative music from the 90s and that kind of stuff. So I started as a guitar player, so every time I learn new stuff, it's really fun to explore new terrain, but then it's fun to see like how it affects the stuff I used to do, or the stuff maybe I'm more I still to this day feel like most at home on a guitar. Even when I've been out of practice and I'm a little slow and sloppy, I still see the guitar and I understand it, really well. So it's like home.
Yeah. I have the same with piano. I think piano and vocal, but especially piano. It's like, okay, different chords, different chord changes, voicings. Very cool piano. All these voicings. Yeah.
Well, we can send people to your website. Would that be the best place? Do you have a preferred way?
Yes, and also I think to the Bandcamp of the album.
Okay.
And on the website, indeed, yes. There's an page on Mikromedas on my website, especially regarding the Mikromedas project. But in general, there's info on the other projects, and also do from time to time online workshops on specializing into different kind of sound synthesis techniques and some arranging and some composition. I have workshops on analog synthesis, frequency modulation synthesis, wavetable synthesis. And I've developed my own, I think, methodology, starting a little bit from the physics point of view. So using a little bit of the physics, but not the formulas, and developing a sort of a core map of how to think about sounds and use that to teach sound synthesis. So, for example, with frequency modulation synthesis in the next edition next weekend coming up, the problem I hear a lot there is that it's very difficult to understand what you're doing with all those algorithms. And I try to find a little bit of a methodology into it, using some science. That's basically,
that's cool. I think it'd be really nice to hear your perspective on that. The sine waves that are often used with FM synthesis, like you're saying, so fundamental to so much in the universe. And they've said that, I've heard anyway, that we still haven't tapped into like half the sounds you can do with like a DX7.
Yes.
It's pretty exciting.
Yes.
Be interested to see your thoughts on that, and love to hear about you going through just frequency modulation.
No. I have a DX7 here, and that's also featured on the album, an old DX7 here. No, we're using for the workshop Dext.
Plug-in,
no, I mean the starting point is of course the formula of FM synthesis. It's basically it's based on Bessel's functions, so there are mathematical functions. But what you have to know, it's a sort of, you could see it as a sort of an extrapolation of ring modulation. That's not frequency, but it's a similar kind of effect. No, I mean the thing is you have to know when I teach it, you have to know a bit of acoustics. For example, if you take a violin, what is the basic sound wave that comes out of a violin? It's a sawtooth wave. But why is it the sawtooth wave? This is because of the physics, and you can rather easily explain it. For example, a guitar, not a violin, a plucked guitar. What is the basic wave shape you would need there? If you look at the physics, you can at a white or blackboard explain it. Well, it should be a pulse wave. So in a square wave with a narrowed, and there's also scientific reasons for it. And that all is connected to the acoustics. So and once you know a little bit of those basic principles, you can use because if you know how FM synthesis works, so you have different algorithms. The most simple is a carrier, and you have a modulator, and you know if you do an FM, you add up harmonic overtones positive to the positive side, and you can also add them to the negative side, which means you flip the phases. You can start doing some math, and then you know, to make, for example, a saw wave on an FM synth, I need is a carrier and modulator with a CM ratio, it's called of 1/1, and I need some feedback, and in this way I will get a sawtooth wave. And this can be the starting point to generate a violin sound, for example. So, but it starts with knowing more about acoustics, and I think that's a little bit underestimated in the world of sound, even on sound engineer. Well, acoustics of instruments. I think music producers do not always know. We had some courses, good courses on that, and of course, being mathematician, of course,
Yeah, it sounds fascinating.
Yeah. And
we'll have to put some links to that in the show notes too. So
yes,
workshops.
Yeah, that would be great. Yes, that would be cool. Yeah.
Well, thanks so much for sitting down and talking. This has been kind of a mind-blowing discussion.
Okay.
I think your work is really, really incredible, and to really get a sense of how far it goes is, it's inspiring. So it makes me want to work on my projects.
Thank you.
And
good to hear.
Maybe one day, I don't know if I'll go quite as far into the universe as you, but
let me know.
Find some new ways to inspire new ideas. It's a great story.
All right. Yeah. Thank you for having me. And so see you maybe next time around.
Yeah, we'll have to definitely talk again. I think there's a lot of places we can go.
Cool.
So thanks again. And thank you everyone for listening. Check out Valery's work. You could go to Valery Vermeulen. That's ValeryVermeulen.net. We'll put that in the show notes, though, so you can just click on the links, and we'll have some other good stuff in there. But so much incredible work, and make sure you check out the album coming out on December 3rd, you said.
Yes, on the label Ash International. Yes.
Ash International. Perfect. Thanks so much.
Great.
And have a great day, everybody. Take care.
Cheers, Bye.